his Nobel Prize winning work was for BCS theory of superconductivity, with which I'm sure many people, if not everybody in this room, is quite familiar. The nanobiophysics theme of this meeting, though, might seem a little bit disconnected to Professor Cooper's famous work. And it sometimes comes as a surprise to physicists to learn that Leon has also made a strong impact on biological sciences, namely neuroscience. And I know this because when I talk to neuroscientists, they're always shocked to find out that there's this fellow named Cooper responsible for the BCM model of neuroplasticity, who actually had some kind of a career in physics before. So without any further ado, let me turn the floor over to my colleague and neighbor next door, Leon Cooper, who's going to be speaking about, does the moon exist only when you look at it?
Thank you, Derek. Thank you, Derek. Thank you very much. It's a really great pleasure to be here. Can you hear me?
No. I think there might be something that needs to come. Oh, it's not a recording.
Okay, so I have to talk into this thing. Oh God. All right. Will both mics work at the same time?
Yes. Is this? So I put the on switch and I turned it up all the way.
Can everybody hear me?
No.
Well, I will just stand here and do a song and dance while they're performing all these technological miracles. I don't need this. I love this part, you know. I'll try to shout.
That's biological system might be the best
Right.
way. There we go. You got something.
This is,
Okay, there we go.
it works now? Oh, okay, boy, wow. Okay, is it working? Yeah, but I don't like to stand here by mic. All right, I'll try.
Do you want to do the MC version? Or?
I'll do something, don't worry. Look, if you can't hear me, please shout. I have to tell you a story about some of my classes. I give these classes at Brown, and there are these kids who sit contentedly in the rear of the room reading newspapers and typing on their computers. At the end of the course, they say, you know, we have these evaluation notices, and they say, you know, everything was okay except he doesn't talk loudly enough. We couldn't hear him in the back of the room. I think, you know, these are these brilliant Brown students. They waited till the end of the term to tell me that they couldn't hear me at the back of the room. Anyhow, if you can't hear me, I'm probably not going to be able to stand here. I'm going to walk around. And can you hear me now? Yes? No? No? All right, okay. Okay, I'm going to sound like, who is it, Colbert? All right, I'll do it, okay. So it's a great pleasure to welcome you here, and it's a great pleasure to talk tonight. And the topic I'm going to talk is does the moon exist only when you look at it? Now this is, you know, you all are practitioners of quantum theory, and you do it brilliantly well, as this conference attests to. But there are problems in the quantum theory that have lasted ever since it began, and these are the ones I want to talk about tonight. So the argument is very old. It goes back to Plato and possibly before. Is there a real world out there that we see imperfectly, according to Plato, for those of you classicists who've read his dialogues, The Republic, as shadows on a screen, Or is the real world a construct that exists only in our mind? A solipsistic position proposed by Bishop Berkeley. Now, as Einstein once said, does the moon exist only when you look at it? And remarkably, this argument resurfaces in a modern context in interpretation, the possible interpretation of the quantum theory. And that's what I want to talk about tonight. Now, possibly you don't realize this, but the essence of the long, continuing, and very famous debate between Bohr and Einstein over the meaning of the quantum theory lies not so much in Einstein's rejection of probability, God does not play dice, but in Einstein's insistence that there's a real world and it is science's duty to describe it. Now, as Pauli wrote to Bohr in 1954, Einstein does not consider the concept of determinism to be as fundamental as it is frequently held to be. Einstein's point of departure is realistic rather than deterministic. Now, what I'm going to talk about tonight is the quantum theory and its interpretations. I'm going to talk about the probability interpretation, the relation between the observer and what is observed, the relation of the theoretical structure to the real world, and measurement. Is the quantum theory complete? And is the quantum theory local? And this is only going to take me about 5 hours to do, so just relax and don't worry about it too much. Now, as you all know, as we all know, in the quantum theory for any forces, the Schrödinger equation gives us the wave function of the system. It's the equivalent of Newton's second law in classical physics, F equals ma. It can in principle be solved for any forces or fields, as you guys have been doing in the course of this conference. And just as Newton's equations, it provides the solution for any physical system. It's the basis for thousands of calculations and used to determine the chemical and the biological properties of systems, and for nanosystems, and for all of the things that we've all been working on, that we're all super experts on doing. But what does it mean? What does it say about the world? And this has been a question of continuing contention since the origin of the theory. And since I have only 30 or 40 minutes, I will clear it all up for you tonight. Okay, so first let's talk about the probability interpretation. Consider an electron moving toward barrier. There's the electron with its associated Schrödinger wave, and there's the barrier. It has detectors placed to record whether or not it penetrates the barrier. And if you adjust the energies properly, it will penetrate sometimes and not penetrate other times. And let's put a detector 2 here and a detector 1 there, and here's the wave going toward the barrier. Now, a classical Newtonian electron would behave, well, classically. If a fast electron would go over the barrier, a slow electron wouldn't quite make it. Here's a fast electron. Here's a slow electron. In Newtonian physics, we'd know exactly what they did. But in the quantum theory, the Schrödinger wave associated with the electron behaves like any respectable wave at a boundary. Part of it is reflected, and part of it is transmitted, like this. So does the electron arrive at detector 1 or detector 2? Or perhaps part of it arrives at 1 and the other part at 2. Actually, this goes back to way, way back in the 20s and 30s in the interpretation of the wave function. But as far as we know, electrons are indivisible. And the essence of the quantum theory is that energy transfers take place in discrete bundles. And this led to Max Born's probability interpretation of the wave function. He says, again, an idea of Einstein gave me the lead. I mean, Einstein gives everybody the lead, and then he objects to the consequences. He wants psi squared to represent the probability density for electrons or other particles. So this means that all the quantum theory can tell us about our electron's eventual destination is that it will sometimes register on the left and sometimes register on the right, depending on how much of the wave function is on the left and the right. Okay, if the experiment is repeated thousands of times, quantum as is most of the case in most quantum theory things with atoms and light transitions and so on. Quantum theory tells us in a natural way the number of right versus left registrations. But for a single experiment, the quantum theory can only tell us that the probability of a right or a left registration. Now, this uncertainty of outcomes is so unpleasant to many physicists. Famous, God does not play dice. Einstein, how do you know what God does? That a variety of other possibilities have been explored, and some of these are called hidden variable theories. For example, the hidden variable in our example might be a yet unseen arrow inside the electron. We don't know what this arrow is, but arrow up leads to transmission. Arrow down leads to reflection. And if we, someday we'll discover what the hidden variable is, and then we'll know it'll be a deterministic theory again. But such theories, as you probably all know, present very serious technical difficulties. In particular, a very famous theorem of John Bell shows that any hidden variable must be non-local. And what is, in my opinion, more important is so far they add nothing to what is already known. So at the moment, it's fair to say that the probability interpretation, with all of its peculiarities and without the hidden variables, is the interpretation accepted by most physicists. All right, but if we accept the probability interpretation, what do we do with the part of the wave function that shows registry on the non-registered side? We have registry here. What do we do with the part of the wave function that shows registry there? Von Neumann and Bohr would agree with Wigner in what is called the Copenhagen interpretation. This famous statement: one must conclude that the only known theory of measurement which has a solid foundation is the orthodox one, and this implies the dualistic theory concerning the changes of the wave vector. It implies, in particular, the so-called reduction of the wave function, wave vector. Once you have the, quote, measurement, unquote, the part of the wave vector that hasn't been measured is thrown away. You've all learned that. That's what everybody learns in their quantum theory courses. However, you can't really support it. It requires that we throw away the part of the wave function that shows registry by a process that does not follow the Schrödinger equation. But such wave function reduction is difficult, if not impossible, to make consistent. That doesn't prevent everybody from being taught that in their courses. But probably all of you were taught that, and you probably teach that to your students, right? Okay. Well, so let's talk about that. So now let's talk about the observer and the observed. One of the problems in the quantum theory is the distinction between the observer and what is observed. Now, John von Neumann, famous mathematical foundations of quantum mechanics, we must always divide the world into two parts, the one being the observed system, the other the observer. In the former, we can follow all physical processes, in principle at least, that is by the Schrödinger equation, arbitrarily precisely. In the latter, this is meaningless. The observer is separated from the observed. And if you will allow me to quote Benedict Baruch Spinoza in his Ethics, they appear to conceive man to be situated in nature as a kingdom within a kingdom, for they believe he disturbs rather than follows nature's order. Okay, now I'm going to illustrate many of these problems by the following, which some of you may think is a too graphic example. But there are no children here, so we'll look at it. So we begin with a single photon, which in my opinion, approaching a barrier with a double slit. And in my opinion, this one experiment which we can do, which we set up in our laboratories here at Brown, illustrates the dark heart of quantum theory. We arrange it so that one photon at a time is released. And these are really one photon at a time because they're separated by an immense amount of time, one photon from the other. So we produce a photon, there's a double-slit barrier, and there's a screen. So here comes the photon, the wave, there's the Schrödinger wave accompanying the photon, looks like that. And when you look at the screen, you see individual registrations here. That we can actually reproduce in the laboratory. But if you do it long enough, you see an interference pattern. And that is one of the deep mysteries of the quantum theory. The photons do not interfere with each other, they interfere with themselves. And they come across the screen and they register beep, 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 and eventually you have an interference pattern. Okay, now we're going to elevate the mystery into what is known as Schrödinger's cat. I'm told that Schrödinger didn't like cats, but he did introduce this. It's wanted, dead and alive, and this I have the courtesy of my colleague Humphrey Maris. And what we do is we connect this single photon apparatus with an infernal device in which Schrödinger's long-suffering cat is imprisoned. And we do it this way. The photon is coming here. If it registers in the upper detector, the poison will be dropped and the cat will die. It registers in the lower detector, the poison will be locked in place and the cat will live. All right. Now, before we set this machine in motion, we draw a shade to spare ourselves the possible suffering of the cat. And now we let the photons go. Now, what you have to remember is the wave function for the single photon apparatus has photons going through the upper slit and the lower slit. And you need both of them to produce the interference pattern. So the wave function has the upper part plus the lower part. You need them, otherwise you don't get the interference pattern. Now, if we include the cat as well as the spectator, the wave function also becomes a superposition of upper and lower parts, like that. All right, now we let the thing go, and now the shade is drawn. In the upper part, the cat is dead. In the lower part, it's alive. Is the poor cat dead or alive? Now this, by the way, excuse me, but I'm just following out the Schrödinger equation. I'm not doing anything very sophisticated here, except I'm doing it in a way that Schrödinger did this originally, and he regarded the outcome as absurd. And of course, it is absurd, but it's not absurd. It illustrates the problem, the quantum theory. So is it dead or alive, or both? If it's dead, when did it die? When the photon registered in the detector, or when the shade was drawn and the observation was made? So part of the problem, and I'm going to reveal the problem to you from my point of view, is the connection between this theoretical structure and the world it purports to describe. In Newtonian theory, if we know the initial conditions of the forces, we can calculate the future motion. And the calculated path can be put into correspondence with the world. So if you think of Newtonian theory, it's like a theoretical structure, and you have theorems and all kinds of things like that, and they can put into one-to-one correspondence with the world, more or less. In the quantum theory, this cannot be done. The wave function, which is completely determined if we know the initial conditions and the forces, cannot be put into direct correspondence with the world. The wave function is a linear superposition of two very different worlds. In one, the cat is alive, and the other, the cat is dead. Both are possible worlds, but the wave function and therefore the quantum theory cannot tell us which world we are in. So, how do we know which world we're in? Why don't we experience two different worlds? If the cat died, when did it die? And what does all this have to do with measurement or observation? So, okay, first of all, what do we mean by a measurement, which is one of the most confusing subjects in the quantum theory? Consider again the single photon arrangement. When can we say that we have measured the position of the photon? What, in fact, do we mean when we say anything has a position? So I would say that it's only when we and other observers agree where it is. It's when everybody can agree where the thing is that it has a position. For the photon, this occurs when there's an interaction with the screen that for practical purposes is irreversible. I'll come back to that. For the moon, on the other hand, always has a position, since all observers, if they look, agree where it is without further interaction. Now, a photon interacting with the screen qualifies as a measurement because the interaction is irreversible in a thermodynamic or a statistical sense. Now, this is one of the important points that I would like to emphasize. What we call a measurement is, in effect, an irreversible interaction of the quantum system with some other system. Sometimes it's a classical system, sometimes it's a big system, but it doesn't have to be. It's often characterized as an observation by an observer thought to be a classical system, or more recently, decoherence due to an interaction with a complex classical environment, but this is not necessarily so. From our point of view, what's required is an interaction that for practical purposes is irreversible. It could be in the interaction of a photon with an atom that ionizes the atom, sending the ionized electron to some distant part of the universe. Now, there's no component of this last system that's particularly classical, but it is relatively irreversible. And that's the key thing, that the interactions, measurement, all of these things that are irreversible are what produce what we call positions and measurements. Now, if the interaction with the screen were easily reversible, we would not consider this a measurement. The upper and lower branches of the wave function could still interfere with each other, and we'd certainly not reduce the wave function to eliminate one or the other. Interactions can be constructed that reverse themselves in seconds, days, years, or the lifetime of the universe. At what point, then, might it be permissible to reduce the wave function in the traditional way? Now, our view is that we never need to reduce the wave function. It may be a linear superposition of two different worlds. In one, the cat is alive, in the other, the cat is dead. Both are impossible worlds, but we're in only one of them. Now, I could add to that, maybe I'll add to that later. So, if the cat died, when did it die? How do we know in which world we're in? Why don't we experience the two different worlds? Do we have to assume the existence of two different worlds, or many different worlds, in Hugh Everett's many-world interpretation? All right, if the cat died, when did it die? In agreement with what we might call common sense, the cat died when the poison was released after as the photon registered in the upper detector, because it's with this irreversible interaction that possible becomes actual in the quantum theory. When it registered here, the list, and then the cat died. When the observer discovers that the cat is dead, affects only the state of the observer's knowledge. He looks, and so he finds out that the cat is alive or the cat is dead. But that has nothing to do with when the cat died. It only affects the state of his knowledge. So how do we know which world we're in? You have two possible worlds there. Quantum theory gives us the two possible worlds. How do we know? We look. That's the only way that we know. There's nothing in the quantum theory that tells us which world that we're in. We just look, and we see which world that we're in. We're either here or we're here. Why don't we experience the two different worlds? Or to paraphrase Wigner, I am sure of the state of my own mind. How could my mind be in the superposition of such two different states? The answer lies in the nature of detectors and minds. The detectors are constructed so that we can have registry in the upper and not the lower, or registry in the lower and not the upper. Otherwise, this way or this way. Otherwise, we wouldn't call them proper detectors. We know the state of our own mind and don't experience two different worlds because there's an almost certain correlation of our own perception between ourselves at different times, as well as an agreement between all observers once the irreversible interaction has occurred. In other words, once you're on one branch rather than the other, there's essentially certain correlation so that you yourself are in agreement with what you saw, and all others are in agreement with you. And that's why you think you know the state of your own mind. So do we have to do we have to assume the existence of two different worlds, Everett's many-world interpretation? No. We only need to assume the existence of one world, the one we're in. And the problem, again, is the relation between the world we are in and the theoretical structure that describes it. The wave function is a linear superposition of two different worlds. In one, the cat is alive, and the other, it's dead. Both are possible worlds, but the wave function, and therefore the quantum theory, does not tell us which world we're in. The branch of the wave function on which we are not describes a possible world that did not happen and that we retain forever. And we can't throw it away because if there's a very short reversal time, we would need it for interference. If there's a very long interference time, we don't need it. And so that's why, for practical purposes, you can do what's called wave function reduction. Now, this reminds me of a famous story by Jorge Luis Borges in The Garden of the Forking Paths that you may or may not have read. He says, in contrast to Newton and Schopenhauer, your ancestors did not believe in a uniform absolute time. They believed in an infinite series of times and a growing, dizzying net of divergent, convergent, and parallel times. Basically, he describes a situation in which you are many different parallel paths that you might have taken in your life, and they all converge together, something that we've all thought about once, and the networks of times which approach one another, forked, broke off, or were unaware of one another for centuries, and embrace all possibilities of time. And I once gave a talk on this subject and concluded it and said, once more, the poet has preceded the scientist, which is very much like the way is this interpretation of the quantum theory. So now I would like to switch gears a little bit and ask the question as to whether the quantum theory is complete. And is it local? So we go back to our classical particle, and it's located at some point, and then it traces out a path like this. And what we all know about a classical particle is you know its speed and where it is as a function of time. And the planets, for example, under the influence of their forces, move in almost elliptical orbits, and at any time they are in particular positions at particular times. Now, a Newtonian particle confined between two worlds would follow a path like this. Again, at any time we know where it is and how fast it's moving. For the quantum particle confined between the same two walls, we have only the wave function and its associated probabilities. The quantum theory does not allow a complete specification of the position and momentum of the quantum particle, which we have all learned and which we all teach our students. Does this mean that something's missing, that the quantum theory, for all its success, does not give a complete description of the world? Now, to answer such questions, Heisenberg introduced his famous Gedanken, or thought experiments. He demonstrated through numerous examples, which may or may not convince you, but we all teach to our students, that it's not possible to simultaneously measure both the position and momentum of a quantum particle, and frankly, this introduced an enormous amount of confusion into the whole question. He says one very accurate measurement of one of these, by the way, Heisenberg changed his view on this later in his life, but I won't go into that. Very accurate measurement of one of these disturbs the system in such a way that increasing uncertainty in the other variable. And so one of these is, suppose you try to measure the position of an electron, you shine light at it, and if you have a long wavelength, you don't locate its position very well, but you disturb its momentum a little. But if you shine a shorter, you've all heard this, and so if the light has a shorter wavelength, for better determination of the electron's position, the momentum of photons is large, producing a greater disturbance of the electron's momentum. So if you try to measure its position, you disturb its momentum. So the way it looks, what does this mean? Does the electron have a position and momentum and trace a classical orbit, but for some reason we can't measure or observe them? Or does the electron not have these properties, so naturally we cannot observe what does not exist? The question is sort of left open by Heisenberg. All right, now Einstein, Podolsky, and Rosen, a very, very famous paper in the mid-30s, EPR, attempted to demonstrate that the electron does have these properties. So since the quantum theory does not, the quantum theory is incomplete. Now, I'm going to give you a variation due to David Bohm, in which we imagine the decay of a pi zero at rest, resulting in the emission of two electrons in opposite spin directions with the total spin equal to zero. The pi zero decays like this, and it gives you two electrons. And since the total spin is zero, one could be up and down or whatever. In any case, the total spin would be zero, and the spin part of the wave function can be written this way, as you've all seen. Okay, now you do this when the electrons are far apart. An observer on the right can measure the spin of the electron on the right. And suppose she measures the spin in the x direction and obtains the value spin up. She then knows that a measurement in the x direction by a partner who's very far away on the left, light years perhaps, will result, or by the way, has resulted, in order to make this Lorentz invariant, because you don't know who did what first, in the spin value spin down. He must obtain this value since the total spin right must be equal to zero. But the observer on the right might just as well have decided to measure the spin of the electron in the y direction or any other direction. Suppose she obtains this result. She cannot measure the spin in both directions due to the uncertainty principle. She then knows that her faraway partner on the left has or will measure the opposite spin for the left electron. Since she could choose either the measurement of the spin in either the x or y direction, she can determine the result of a measurement her partner on the left can make or has made, even though he may be light years away. That's essentially the Einstein-Podolsky-Rosen paradox. Such correlations, by the way, have actually been observed in an experimentally accessible situation involving two-photon atomic transitions by Aspect, Grangier, and Roger. Actually been observed. So EPR conclude either the electrons possess an x and y spin in reality, or a measurement on the right can influence what happens on the faraway left. In Einstein's words, spooky action at a distance. Don't forget, they're very, very far separated from one another. Now, from our point of view, the point of view that I've been trying to present, her choice of measuring the x or y spin involves interaction, an irreversible interaction, after which the electron can be said to have a precise x or y spin. Before that interaction, it can't be said to have any spin at all. It's only after the irreversible interaction that it has an x or y spin. It is the irreversible interaction any place that determines what universe we are in with all the correlations that result, but the correlations that were always there in that universe. So if the observer is part of the system, part of the wave function, quantum theory tells us the probability of her choice, x or y spin, then we are in one branch or other with all of the resulting correlations that were always there. And so I ask you, in that situation, is there any non-locality? This is the part that I leave as an exercise for the audience. However, if she's not part of the system, if she exists as an observer on the outside, then her free choice at some place determines the universe everywhere. And this does appear to be non-local. So, can we conclude that an observer outside of the system with free will is inconsistent with locality? Let's say if you have an observer that is part of the wave function, maybe it's local. But if she's outside of the system, then it does seem to be non-local. Such questions are so puzzling that Richard Feynman was led to say, "We've always had a great deal of difficulty understanding the worldview that quantum mechanics presents. I cannot define the real problem, therefore I suspect there's no real problem. But I'm not sure there's no real problem." Or perhaps Spinoza had it right. Men believe themselves to be free simply because they are conscious of their actions and unconscious of the causes whereby these actions are determined. I have to say that thousands of papers have been written on this subject, but two that have particularly informed this talk are the relative state formulation of quantum mechanics by Hugh Everett and the interpretation of measurement of quantum theory done by myself and Deborah Van Vechten in the American Journal of Physics in 1969. Deborah was an undergraduate here at Brown, and I'm very proud of that paper. And also I have special thanks to Pete Bilderback over there, who created all of the animations that you enjoyed so much. And, by the way, the moon does exist, even when you don't look at it. Thank you.
I can't imagine that there are any questions after that. But in case there are a couple of questions, we'll be, yes, Larry.
When people talk about the observer and the wave function of the observer, I'm always a little confused about that, because I know